The internet glance is so far away that it is catching light that has already been voyaging for over 13 billion years. Yet the universe has been extending, and thus, since then, the light has been spreading. Most distant worlds, we're thinking back in time nearly to the Big Bang. The vastness of the universe might appear immense, but it began in its entirety from our reference to the singularity. As of now, this is how we might interpret the Big Bang hypothesis. Nevertheless, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. The renowned physicist Brian Cox has proclaimed that the noteworthy discoveries of the JWST might actually alter our perception of the entire universe. Join us as we delve into these brand new discoveries about the heavens that promise to alter our understanding. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, stands as a wonder in currently ongoing galactic investigation. The telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope. Thanks to a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its predecessor. It employs cutting-edge design and technology, enhanced for concentrating on the universe in incredibly fine detail. Unlike the Hubble, the JWST conveys clear and sharp pictures of far-off heavenly bodies, working primarily in the fascinating infrared range. This component enables it to penetrate astronomical relics and divine objects that were previously hidden from our perspective. With its enormous 6.5-meter primary mirror made of 18 hexagonal sections, the JWST dwarfs Hubble's reflector size. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits in harmony with the Sun and Earth, ensuring a constant and steady view of the universe. As seen from far off the edges of the universe, it not only explores light-years of distance, it also involves a type of time travel. The JWST uses infrared instruments to observe heavenly objects and events going back billions of years. The light emitted by these objects, because of the expanding universe, undergoes redshift, moving from the visible range to the infrared frequency. Luckily, the JWST can detect this infrared light from distant heavenly bodies, enabling researchers to investigate the birth of stars, study galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves locating an unfathomable mass of cosmic systems at the edge of the observable universe. This finding challenges the validity of current theories on how things came to be, provoking a reassessment of our key cosmological assumptions. To better understand how we got to this point, we should take a short excursion through the history of space exploration. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by observing celestial bodies. In the 17th century, Newton's laws gave a conceptual framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made revelations in cosmology and observational space science. His observations uncovered that far-off nebulae were actually distant galaxies far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving at higher rates, demonstrating the universe's expansion. World War II signified the start of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit. Then came Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969, both rapid and monumental accomplishments. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of our understanding of the universe. The Hubble Space Telescope, for instance, snapped the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, which captured a vast number of galaxies in what appeared to be an empty patch of space. The HST also examined exoplanet atmospheres, identifying organic and water-based molecules, and pointing to the possibility of habitable zones beyond our solar system. It provided insight into the supernova SN 1987A and the life cycle of enormous stars. These achievements cemented the Hubble's legacy as a foundation of modern cosmology, astonishing the entire world with its enormous discoveries. The James Webb Space Telescope was launched to expand on the advancements in technology and knowledge from Hubble. It represents our understanding of the universe's origins, currently explained by the prevailing theory that the universe began around 13.8 billion years ago. According to this theory, the universe started as a hot and dense singularity. Rapid expansion followed, giving rise to energy and matter. As the universe cooled, atoms formed, followed by stars, galaxies, and the structures we see today. The Big Bang theory also explains cosmic microwave background radiation, element abundance, and the large-scale structure of the universe. Despite its wide acceptance, the theory faced skepticism and challenges in its early days. Alternative models like the steady-state theory suggested a universe without a specific beginning. Concerns about evidence for the singularity's initial expansion and observed anomalies were raised. Most of these objections were addressed over time. A significant piece of supporting evidence came in 1965 with the detection of cosmic microwave background radiation. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. Their precise measurements of the microwave background matched theoretical forecasts remarkably well. Enter the James Webb Space Telescope, equipped with advanced instruments that can observe in the infrared through cosmic dust. Working primarily in the infrared range, JWST captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities allow it to focus on star-forming regions, celestial nurseries, and the formation of stars hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, can penetrate dust clouds from other stars, overcoming a major limitation of the Hubble Space Telescope. The JWST can also observe cooler objects that emit mainly in infrared light, making it ideal for researching exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward red's longer wavelengths. These redshifted signals can be detected using the JWST's infrared capabilities, capturing light from the beginning of the universe and offering insights into its formation and evolution. Intense events like black hole mergers or the births of new stars primarily occur in the infrared range, further enhancing the JWST's investigative capabilities. This telescope allows us to peer into regions that would otherwise be invisible or hidden, giving us a deeper and more comprehensive view of cosmic history. The puzzling part is that we're still unsure how such galaxies could form so early. These galaxies are far too massive and evolved for the short span of time following the Big Bang. According to our current models of cosmology, galaxies should form gradually, beginning as small, irregular clusters of stars and dust that grow and merge over billions of years. Yet the JWST has shown us enormous, mature galaxies existing just 300 to 500 million years after the universe began. This stunning revelation has forced scientists to question fundamental assumptions. Are we missing key elements of galaxy formation? Could dark matter and dark energy be behaving differently than we thought? Or is there a flaw in our understanding of the timeline of the universe's early stages? One possibility is that the processes of star formation and galaxy assembly were much more efficient in the early universe than we previously believed. Alternatively, there may be unknown physics at play, perhaps new particles or forces influencing cosmic development. The James Webb Space Telescope is not only providing new data, it is shaking the very foundation of cosmic theory. Its observations have introduced tension between what we expect and what we now see. The so-called impossible galaxies challenge the standard model and could eventually lead to a revolutionary new paradigm in cosmology. Moreover, the JWST's capabilities extend far beyond distant galaxies. It has already begun probing the atmospheres of exoplanets, some of which are located in their stars' habitable zones. By analyzing the infrared light passing through these atmospheres, scientists can detect the presence of water vapor, carbon dioxide, methane, and even potential biosignatures. This opens the door to answering one of humanity's most profound questions. Are we alone? With its advanced spectroscopic tools, the JWST could potentially identify planets with the right conditions for life: rocky surfaces, water, and stable temperatures. As we explore more of these exoplanets, we edge closer to identifying a true Earth twin or even finding signs of extraterrestrial biology. In essence, the James Webb Space Telescope is not just a machine. It's a time traveler, a cosmic archaeologist, and perhaps a harbinger of a new scientific era. Its launch marks not only the next step in space exploration, but also a deeper step into our understanding of existence itself. Every image it sends back, each speck of light from the distant past, is a message from the universe, inviting us to rewrite the story of creation and evolution. Enormous structures formed so early in the universe's history might lead us to reconsider our knowledge of the formation and development of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic ancestors. The JWST can acquire insights into how stars in galaxies, and over time, planetary systems, developed and changed over billions of years. These observations also contribute to more general inquiries about the fundamental nature of the universe, including its elements, structure, and the factors that control its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light from galaxies that once existed. Telescopes were based on visible and ultraviolet light observations, making it challenging to explore the early universe where these wavelengths are absorbed or distorted by interstellar gas and dust. The James Webb Space Telescope signifies an important leap ahead. When looking at galaxies from the universe's early stages, the JWST, in contrast to its predecessors, can observe the formation of celestial objects within the next few hundred million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered numerous ancient galaxies, providing remarkable detail and clarity in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data poses a number of challenges to aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand the structure and evolution of the universe. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the beginning of the universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appeared more developed than expected, challenging conventional models that forecast slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than initially considered. These observations raise fascinating questions and avenues for further exploration. The existence of large structures in the early universe challenges current models of cosmic structure formation, prompting researchers to refine their models for better explanations. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental cosmological concepts. Substantial differences in the conditions of the universe's early days, in contrast to predictions made using existing models, have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. All we can do at the moment is say that additional research is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the cosmos, but in-depth investigations sometimes reveal differences. For example, early observations may reveal particular properties or arrangements within distant galaxies that, upon closer investigation, show alterations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require meticulous investigation in order for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is one illustration. By analyzing the light emitted or absorbed by astronomical objects and examining its characteristics, spectroscopy provides detailed information about the chemical composition, temperature, density, as well as the motion of celestial bodies. This analysis helps us understand the origins, growth, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed. For instance, initial observations of distant galaxies primarily suggested a straightforward structure dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic examination with the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood. This defies conventional thoughts on the universe's early chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similar initial assumptions about galaxies in the early universe were founded on preliminary indications pointing to a fairly regular pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex variety of chemical compositions in these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures such as the presence of carbon dioxide, water, methane, and other organic compounds. These findings provide valuable perspectives on the potential habitability of exoplanets and the conditions that might support life beyond our planet. As well as exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are encircled by dense gas clouds and dust, areas which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the smallest glimpses of these newly formed stars as they emerge from the shadows, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another outstanding feature of JWST research is its ability to peer into black holes in galaxies' hearts. Particularly, supermassive black holes are believed to reside at the centers of the majority of large galaxies. The JWST's advanced instruments allow scientists to observe how matter behaves around black holes, providing new insights into their expansion and impact on galactic evolution. The powerful jets of energy they produce help astronomers piece together how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST's discoveries are not only answering long-standing inquiries but also bringing new ones. As it investigates the universe's past, it is revealing phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current models of the cosmos and open up new research avenues that were previously unimaginable. The discoveries of the JWST are not merely pushing the boundary.